So what we did talk about, just to remind everybody before we jump into a problem, is if you're looking at extreme values of any sort, minimums and maximums, whether absolute or local, one place they can occur at is endpoints, because if you ignore that, then that would be a max. They can occur when the first derivative is equal to 0. I'm not drawing very straight lines, but those are places where the first derivative is 0. They can also occur at sharp corners. Those are where the first derivative is undefined or does not exist. And then they can occur again at endpoints like that. And we did have a theorem that said that's it. Nowhere else can they possibly occur. So when you're searching for these, you don't have to sit there and look at every single point possible. You just have to look at endpoints and then look at the first derivative as 0 or undefined, and that's it, nothing else. So you're not searching everywhere. We saw critical values, critical numbers, critical points, all means the same thing. When they say to find those, that's when you take the first derivative and set it equal to 0. See where it does not exist or it's undefined. And those x-coordinates, that's what they're looking for, is the x-coordinates. So when we talk about critical numbers, that's it. Derivative equals 0 or undefined. Find x. I think that's it. Seems like we sure did a lot more than that. But that's it in a nutshell. We did the polynomial, and it was nice because polynomials are nice. And now we're going to do number 72, which is not a polynomial, and it's not very nice. But we're going to do. We're basically, again, going to be looking for the absolute extrema. I'm not sure what the direction was saying. As far as the local extrema, algebraically, we focus more on that in 4.3. We can kind of look at it a little bit for this problem, but 4.3 is really mostly focused on the local extrema. And 4.1 is more focused on absolute extrema. There's slightly different techniques. But we'll look at them a little bit while we're here with this problem. From the beginning, though, let's look at this. And like I said, this problem will probably take up almost a full page. So when you get things that are not polynomials, sometimes they get a little messy. But let's start off by talking about the domain of this problem. When we did the polynomial last class, if you remember, it seems like that was forever ago. Polynomials, again, do not have endpoints. They do stuff like this. So we didn't have to worry about endpoints with the really only other problem we did. So this one, because it's a square root function, will have an endpoint to it. So again, whatever's underneath the square root, that's all we care about. What's underneath the square root cannot be negative. So we start with that. We don't care about the x squared. If all you had was an x squared function, I mean, that's a domain of all real numbers. So we don't worry about that. We just worry about the square root part, because that's got restrictions on it. And then we solve this for x. So we do have one endpoint. The other one, obviously, it's half open, half closed. So we do have one endpoint, and again, the only reason we really want to focus in on that, back to my drawing over here. If you do have an endpoint, that's potentially an absolute value. Like on that one, it's an absolute max. All right, so before we get into the derivative, then questions with that piece? We need to take the first derivative. We'll set it equal to 0 and see where it does not exist. So first derivative. All my colors are down there. First of all, we do have a product, so we will be using the product rule. Secondly, and you don't have to rewrite this, hopefully you can do it in your head if we've been doing enough of these, but secondly, we have a composition also. We do have 3 minus x all raised to the 1/2 power, so we will be using the chain rule on that also. But let's start with the derivative of x squared. So again, just the product rule. Derivative of x squared times the rest of it. And then the other half of the product rule, keep the x squared and use the chain rule. So we'll start with the 1/2 power. So bring the 1/2 out front. The new exponent is a negative 1/2. And then times the derivative of what's inside. And our derivative is done. So we'll take this in steps. Questions with the derivative? I'm kind of writing uphill. Now from here you have two different choices. I'm going to factor because I like that method. Now I saw Michelle did this last Wednesday. And she put this down as a fraction and did common denominators, and it works out perfectly. She did it, you can see her work. But I'm going to factor because I like that method. But as I've said, probably all semester long, hopefully, with algebra, a lot of times you do have options, so go with what you're comfortable with. I'm going to factor though. And we haven't done a whole lot with factoring the negative exponents. I know we've come up, I can think of once only, so we'll go through this slowly. But the idea with the exponents, you have a 3 minus x to the 1/2 and a negative 1/2. You always want to take the smallest exponent that you see out. So we'll factor that out. I got 2. You could factor the 1/2 out also, but I'll just focus on one thing at a time. All right, now the thing is, again, when we factor, we subtract exponents, and so I would take 1/2 and subtract a negative 1/2, and the key is you have to subtract it. So I'd be like, in your head, the old exponent, you subtract the thing you just factored out, and that gives you the new exponent. So all together. And right now, just so you know what I'm doing, I'm just focused on this term. I'm just looking at that term only. So I factored, I have the 2 still left. The x came out. And then it's 3 minus x. My new exponent is a 1. And then we move on. So questions with that first half? I still got to do this half. Well, let's the other side goes faster, I think. We're factoring out an x and the 3 minus x's, so what I have left would be another x, a 1/2, and a negative 1. And technically speaking, it is completely factored now. We certainly could clean this up here in the middle, but it's factored. To be completely factored, it just has to be x times this times this. That's all factoring means. It's all multiplied together. So before I go on, questions on that phase? So, what we are looking for is these spots. Where is the first derivative equal to 0? So we're going to set that equal to 0 and solve it. Since it's completely factored, I can break off each step. Just take each factor, set each factor equal to 0. So the first factor is just the x. That's done. There's our first critical number. We set the second factor equal to x. And when you're doing this, you can just set the factor equal to 0. You don't have to worry about the exponents. We can just set the factor itself only. If you want to include the exponents, you can. You'll get the same answer in the end. But you really just need to set the factor itself equal to 0 and then solve it. And one more factor. So now we set this factor equal to 0. I eventually, one point or another, I'm going to have to clean that up a little bit, but I'll do it now. So that's my third and final factor, set equal to 0, and solve for x. So I'll combine, I'll subtract the 6 to the other, well, I'll subtract something. Solve for x. Negative 2x minus 1/2 x gives me a negative 5/2 x. And divide both sides by 5/2, and we would get 12/5. So we got 3 critical numbers, so we'll stop there for a moment. Questions with getting the 3 critical numbers? As you notice, one of the critical numbers is also the end point, so we kind of got double duty going on there. We have these other 2 critical numbers. Just make sure that any critical numbers you get are actually in your domain. You don't want to find a maximum that's doesn't exist. So both of those are in our domain, so we're good. What else do I want to say? Oh, the part over here, back to this. We always, say find where the derivative is equal to 0, and also find where the derivative is undefined. That's sort of built into this process, even though I didn't specifically say anything about it being undefined. When I set this factor right here equal to 0, because this factor has the negative exponent, and we know anytime you have a negative exponent, a negative exponent means that it is in the denominator. And so by taking that factor and solving it, that x equals 3, that gives me where it is undefined. So this whole process does take into account where is the derivative 0 and where is this one here is where the derivative was undefined. So it's all built into the process. So we're going to go on to evaluating each of these critical numbers, but everybody good up to here? So move on to the last phase. When we are looking for the extreme values, now we had the extreme value theorem, and that said if we're on a closed interval, we're not, but if we're on a closed interval, we're guaranteed an absolute max and an absolute min. We're not on a closed interval, we're on It's half closed, half open. So we're not guaranteed absolute values, but we are going to get some. So, and this is where I graphed this yesterday. I have my calculator. So let me see if I can remember. I remember roughly what it looks like. We're going to go back and look at the endpoints and stuff still, but all right, I got to graph it again. I've been using my calculator. It has this interesting bump to it, which you don't know unless you kind of already have this planned out. Let me see if I can get this. All right, I am a little bit slow today. Oh, we'll get there. You know, I'd probably be faster if I just use my memory. All right, my domain was negative infinity to 3. So let's go. Hey, my calculator is slower than I am. Oh, let's see. Okay, so it starts off somewhere here, goes up, down, that. There you go. Thank you. Now, first of all, let's just talk about this. We already said that the domain went from negative infinity to 3. 3 is a closed endpoint. That's not a great drawing, but it'll get us where we want to go. What we can see is, just to recap again, when you do have a closed endpoint, those are candidates for extreme values, minimums, and maximums. That was my domain again. So the closed endpoint was a possibility for an extreme value, and we can look at it now and see that at least it's a local minimum. We'll kind of check to see if it's an absolute minimum also. Because we had an open endpoint here, as you can see, that does not give us an extreme value. The open endpoint means that that keeps growing, forever. So we will not have an absolute maximum. Because it depends on the circumstance, but because the way this function goes, it grows forever, we won't have an absolute maximum. And we probably could have predicted that from the original function. Again, if you ignore the square root, we know that y equals x squared, that's going to grow forever. That's how the function is. So let's go back to getting those endpoints then. So when we get to this last phase, to find the extreme values, we're looking for the y-coordinates. Remember, extreme values, we're talking about the high point and the low point, so you got to get the y-coordinates for that. So we're going to go back and plug it into here. So we do want the y-coordinate, not the slope. dy dx gives you slope. We don't want that right now. So plug it into there. Oh, good grief. How much room can I take up? Now, I wrote, this is a general statement. My critical number and one of my endpoint, my only endpoint, there's overlap there. But this is what I need to evaluate. I'm going to write it as f of, just for my sake. So we just want to find what those y-coordinates are to get, again, max and min values. Okay, zeros are easy, 3 is easy, 12/5 is not so easy. I got the old calculator. Everybody get a 12/5 on theirs? I don't remember. There it is, trace. Looking for my trace button. 2.4. I round it off eventually to that. I'll say. Actually, it's pretty good. All right, I think you got them all labeled. So back to absolute extrema, where there's no absolute maximum because this function does grow forever. There is an absolute minimum, which is 0. As far as local minimums and maximums, like I said, they get a little bit more into the algebra behind it in 4.3. So right now we're just sort of looking at it more graphically speaking. That, again, it still occurs at these derivatives and stuff like that. But we do have a minimum, maximum, minimum, and that's it. So this point right here would give me a local maximum. It's just not an absolute maximum. All right, now this one again did have much messier algebra involved, but the steps again stay the same for all these problems. So questions with the steps. I might just have you guys work them now. There's some problems on there for you guys to try, but probably maybe a better thing if you want to start working on the problems that are for points. That's probably more motivated to do that. So, does anybody need an extra copy of the problem?